Okay, looking at this problem, I'm thinking right away to make a u substitution because I recognize that the derivative of tangent is secant squared, so that should work out nicely. So why don't we let u equal the tangent of theta halves. So then right away du, the derivative of tangent is secant squared of the same thingy times the derivative of the inside by the chain rule. And the derivative of that would be 1/2 d theta. And if you compare and contrast what you have, I don't want the 1/2 there, so let me actually multiply both sides by 2. I'll put a 2 there. So the 2 knocks out the 1/2. Now I think I'm actually ready to rewrite this. And I'll temporarily just ignore these guys, the limits of integration. I'll just forget about them for a moment. Let me just rewrite this. So this here, that is u times, and then secant all this gibberish, so that is u, and all that is all of this, right? Which is 2 du. So I'm gonna write du there, and I'll put that 2 in the front. And then so this is just, let me write this a little nicer. So this equals this, which equals that. And then I'll just take the antiderivative of u, and then the antiderivative of u is 1/2 u to the power of 2. And the 2 and the 1/2 knock out, so it's just u squared. But then remember that u is that there. So this is tangent of theta halves, quantity squared. And this is to be evaluated from pi over 3 to pi over 2. And you know what to do. You can just plug this in, but I'll do it nonetheless. So I did some stuff here, and I got a value of 2/3 to be the final answer. So that's what I got for this problem here. So the key was to use a u substitution. Now for this one here, I would use a trigonometric identity. So here is a fact, one of the many different trig IDs, and it's a power reduction formula. I think that's what it's called. This is a good handy dandy formula to know because it takes something that's squared and it reduces it to something that's not squared. So let's compare and contrast. Let's try to apply this technique to our expression. So this is just the general rule, but ours says this. So let me write what we have directly below its counterpart. So based on what you see, this is what we have. What would this look like on this side? Well, it's still 1/2. 1 minus, and it's cosine. So look at the comparison. This is 2 theta, this is theta, which means that whatever this is, you times it by 2, boom, copy and paste. So if this is theta, that's 2 theta. If this is like 5, then this is 10. If this is w, this is 2w. If this is x over 2, this is twice that much, which is just x, because of course you just multiply it by 2. So by substitution, that I'm going to turn it into this. So let's go back to the main problem here. So this is the same as that there, but instead of sine squared x halves, we're going to go 1/2 1 minus cosine x dx. We no longer need that. Let me go ahead and kick the 1/2 out to the front. And I think from here, you're good. It's just a matter of doing that initial manipulation. Let's take antiderivatives now. So that'll be x minus sine x, right? Because if you take the derivative of this, it should be that there. And we're going from 0 to pi over 2. So let's just plug these in. So here's actually what I got. 1/2 pi over 2 minus 1. If you want, you could actually take out a 1/2 from there. That'll be like 1/4, and then it'll be something like pi minus 2. So these are the same thing. So it doesn't matter how you turn it in. So I'll just submit this. So this would be the final answer for this one here. And for something like this is a very technical problem. By technical, I mean there's a lot of notation that should be carefully produced. Let me just show you how I would do this and how to get the final answer, okay? So let me write this down again. So we have capital F of x equals this integral expression here. And they're almost always presented, that's a plus, that's a t. They're almost always presented in such a way that the lower limit is a constant and the upper limit is a variable expression. Now we want f prime, this is the goal. That's the goal right there. So what we need is we have capital F, we just need the derivative. So we have to take the derivative of both sides. So if I take the derivative of this, it literally becomes capital F prime of x. If I take the derivative of this, it's gonna knock out it's going to knock out the integral symbol. All that's left is this here along with the evaluation of these limits. So watch what I do. I'm going to go dt over 3 plus t, and this is going to be evaluated from 1 to x squared. So when you take the derivative of something like this is just a title. The derivative will knock out this symbol. You just have this inner function evaluated with its limits. And now watch what this is. So when you plug an x squared into here, it's more than just that. Watch what I do here. I'm going to go 1 over, but then I'm going to multiply by 2x. Let me tell you why. Because there's a 1 right here, and that 1 is there. And the bottom is just, you can see the bottom. T becomes x squared. But that dt is the derivative of the object that you plugged in, the input. The derivative of x squared is 2x, and that covers your dt. And then minus, and do it again, 1 over 3 plus 1, because now I'm plugging in 1, times 0, because dt is the derivative of your input, which is just 0. And so, of course, this is just gone. And so final answer, this here. So, lesson to be learned for a problem like this that's structured in this way. If the lower limit is a finite value, a constant, then that's going to go away because of the derivative of that constant, which eventually pops up. So it's really just plug in the upper limit and then multiply by the derivative of that upper limit. But yeah, there's a lot of fancy notation that I omitted. Nonetheless, this is the result.